The observatory was quiet, save for the soft hum of cooling fans and the occasional beep of monitoring equipment. The astronomer sat alone, her eyes fixed upon a screen filled with distant galaxies, each one a swirling collection of billions of stars, each one moving away from our own. She had spent decades tracking their motions, watching as they retreated further and further into the darkness. But tonight was different. Tonight, her calculations had revealed something unexpected, something that made her question everything she thought she knew about the fate of our universe. The galaxies weren't just moving away, they were accelerating, as if driven by some invisible force that grew stronger with distance. The implications were staggering. If this pattern continued, if this mysterious force persisted, then eventually every galaxy, every star, every planet would be driven so far apart that the night sky would become an empty void, devoid of light, save for the stars of our own galaxy. The astronomer leaned back in her chair and wondered, where is everything in the universe going? That question, where is everything in the universe going, is one that has puzzled humanity since we first looked up at the night sky. For most of our history, we believed the universe was static and unchanging, a perfect celestial machine ticking along for eternity. But in the early 20th century, this comfortable assumption was shattered by a discovery so profound that it fundamentally altered our understanding of the cosmos. The universe, it turned out, is not static. It's expanding. And this expansion has profound implications for the ultimate fate of everything within it. The story begins with an American astronomer named Edwin Hubble. In the 1920s, while working at the Mount Wilson Observatory in California, Hubble made two groundbreaking discoveries. First, he proved that the fuzzy nebulae that astronomers had been observing were actually distant galaxies, island universes, similar to our own Milky Way. But his second discovery was even more remarkable. By measuring the light from these galaxies, Hubble noticed something peculiar. The light was stretched, shifted toward the red end of the spectrum. This red shift was more pronounced in more distant galaxies, leading Hubble to an astonishing conclusion. The universe was expanding. Think of the universe as a loaf of raisin bread dough rising in the oven. As the dough expands, each raisin moves away from its neighbors. From the perspective of any particular raisin, all the other raisins appear to be moving away, and the farther away a raisin is, the faster it appears to be receding. This is precisely what Hubble observed with galaxies. Every galaxy is moving away from every other galaxy, and the farther away a galaxy is, the faster it's receding from us. But what drives this cosmic expansion? For decades after Hubble's discovery, scientists assumed that the expansion would eventually slow down. After all, gravity pulls things together, and all the matter in the universe exerts a gravitational attraction on all other matter. It seemed logical that this collective gravitational pull would act as a brake on the expansion, perhaps even reversing it entirely, leading to what astronomers called the Big Crunch, the opposite of the Big Bang. However, in 1998, two independent teams of astronomers made a shocking discovery. They were using Type Ia supernovae, incredibly bright stellar explosions, as standard candles to measure cosmic distances with unprecedented precision. What they found defied expectations. Not only was the expansion of the universe not slowing down, it was speeding up. The universe was accelerating in its expansion. This discovery was so unexpected, so counter to the prevailing wisdom, that one of the astronomers, Brian Schmidt, initially thought they had made a mistake. My own reaction was, "Oh no, I've made an error," he later recalled. But the data was clear. The universe was indeed accelerating, driven by what scientists now call dark energy, a mysterious force that permeates all of space and pushes galaxies apart with ever-increasing strength. The discovery of dark energy has profound implications for the ultimate fate of our universe. If the acceleration continues, and all current evidence suggests it will, then the universe is headed for a state often called the Big Freeze, or heat death. In this scenario, galaxies will be pushed so far apart that they will eventually become invisible to one another. Stars will burn out, black holes will evaporate through Hawking radiation, and the universe will become an increasingly cold, dark, and empty place. Indeed, this process has already begun. The observable universe, the portion of the cosmos from which light has had time to reach us since the Big Bang, is currently about 93 billion light-years in diameter. But the actual universe is likely much larger, perhaps infinitely so. And because of the accelerating expansion, there are already galaxies whose light will never reach us, no matter how long we wait. They are forever beyond our cosmic horizon, receding faster than light can travel through the expanding fabric of space. And so we find ourselves in a universe that is not only expanding, but accelerating, with profound consequences for the future of everything within it. But to truly understand where everything is going, we need to examine not just the largest scales of the cosmos, but also its smallest components. The fate of matter itself, the atoms and particles that make up everything from stars to planets, to our own bodies, is inextricably tied to the expansion of the universe. Let's start with the stars. These cosmic furnaces are the universe's primary factories, forging heavier elements in their cores through nuclear fusion. Our own sun is currently about halfway through its 10 billion-year life as a main sequence star. In about 5 billion years, it will run out of hydrogen in its core, swell into a red giant, and eventually shed its outer layers to form a planetary nebula, leaving behind a dense Earth-sized remnant called a white dwarf. This is the fate of most stars in the universe, those with less than about 8 times the mass of our Sun. But more massive stars meet a more spectacular end. When they exhaust their nuclear fuel, they explode as supernovae, briefly outshining entire galaxies. The most massive stars collapse into black holes, regions of space where gravity is so strong that nothing, not even light, can escape. Black holes themselves have a life cycle. Over enormous timescales, we're talking about 10^67 years or more, they will evaporate through a process called Hawking radiation, named after the physicist Stephen Hawking, who first predicted it. As the universe continues to expand and cool, even these mysterious objects will eventually disappear. But what about the ordinary matter that makes up planets, moons, asteroids, and comets? What about the matter that makes up living organisms like ourselves? Its fate, too, is bound up with the expanding universe. In the very long term, even atoms themselves will decay. Protons, once thought to be absolutely stable, may actually decay. With a half-life of around 10^34 years, though this remains theoretical and has never been observed, if proton decay is real, then all matter as we know it will eventually dissolve into radiation, leaving nothing behind but a thin gruel of photons and leptons spreading through an ever-expanding cosmos. Of course, these processes occur over timescales so vast that they defy human comprehension. The universe is currently about 13.8 billion years old, a mere infant compared to the quadrillions, quintillions, and even larger numbers of years over which these future events will unfold. Our own species has existed for less than 1 million years, and our recorded history spans only a few thousand. The fate of the universe will play out over durations literally trillions of times longer than human civilization has existed. And yet, Despite the vastness of these timescales, scientists can make these predictions because the laws of physics appear to be constant. The same equations that govern the behavior of particles in our laboratories also apply to distant galaxies and black holes. The same principles that describe the expansion of the universe today can be extrapolated to predict its state billions and trillions of years into the future. But there is an important caveat to all of these predictions. They assume that our current understanding of physics is correct and complete. History suggests that this is unlikely. Just as Newton's laws of motion were later refined by Einstein's theory of relativity, our current theories may eventually be superseded by more accurate models. Dark energy, in particular, remains poorly understood. We know it exists because we can measure its effects on the expansion of the universe, but we don't know what it is or why it has the particular strength that it does. There is also the possibility that the nature of dark energy could change over time. If it were to become stronger, it could lead to a scenario physicists call the Big Rip, where the accelerating expansion becomes so violent that it tears apart galaxies, stars, planets, and eventually atoms themselves. Conversely, if dark energy were to weaken or reverse, the universe could stop expanding and start contracting, leading to the Big Crunch scenario mentioned earlier. There's even a speculative idea called the Big Bounce, which suggests that a contracting universe might not end in a singularity, but rather bounce back into a new expansion phase, perhaps giving rise to a new Big Bang. And so, the true answer to where everything in the universe is going is that we don't know with absolute certainty. We have well-supported theories and models that make specific predictions, but these are based on our current understanding of physics, which is inevitably incomplete. The universe has surprised us before, and it likely will again. What we do know is that on human timescales, tens, hundreds, or even thousands of years, the universe changes very little. The expansion that will eventually drive galaxies beyond our cosmic horizon takes billions of years to produce noticeable effects. The stars that light our night sky will continue to shine for millions to billions of years. Even our own sun has another 5 billion years of stable burning ahead of it. But if we zoom out to cosmic timescales, the picture changes dramatically. The universe we observe today is just a snapshot, a brief moment in a grand cosmic evolution that stretches far into the past and even further into the future. And what a future it is! A future of ever-increasing emptiness, of galaxies isolated by the relentless expansion of space, of stars burning out one by one until the cosmos becomes a cold, dark void, or perhaps not. Perhaps our understanding will change. Perhaps new discoveries will reveal a different fate for our universe. The history of astronomy is filled with paradigm shifts and unexpected revelations. From Earth-centered to Sun-centered models of the EEE, solar system, from a static to an expanding universe, from a decelerating to an accelerating cosmos, our understanding has evolved dramatically over time. It would be presumptuous to assume that we now have the final answer. Indeed, some of the most exciting developments in theoretical physics today involve ideas that could completely transform our understanding of the cosmos. String theory, for example, suggests that our universe might be just one brane. Think of it as a membrane floating in a higher dimensional space alongside other branes, other universes with potentially different physical laws. If true, this could mean that the fate of our universe is bound up with these other universes in ways we can't yet comprehend. Another fascinating possibility comes from quantum mechanics. The many worlds interpretation suggests that every quantum event creates a branching of the universe into multiple realities. If true, this would mean that the future isn't a single path, but a vast tree of possibilities, with each branch representing a different outcome of quantum events. And then there's the simulation hypothesis, the idea that our entire universe might be a complex computer simulation created by a more advanced civilization. If true, the fate of our universe would depend on the intentions and capabilities of these hypothetical simulators. They might keep the simulation running indefinitely, or they might terminate it once it has served its purpose. These ideas might sound like science fiction, and to some extent they are. They're speculative, pushing the boundaries of our understanding. But they're also based on serious scientific theories and mathematical models. They remind us that the universe might be not just stranger than we imagine, but stranger than we can imagine. But let's return to what we know with greater confidence. Based on our current understanding of physics and astronomy, the expansion of the universe will continue to accelerate. Galaxies will recede from each other at ever-increasing speeds. The cosmos will grow ever more diffuse, ever more empty. On an even longer timescale, matter itself will change. Stars will burn out. Black holes will evaporate. Protons may decay. The complex structures that define our current universe, galaxies, stars, planets, life, will give way to simpler, more elementary forms. This vision of the far future can seem bleak, even nihilistic. A universe that ends not with a bang, but with a whimper, fading into darkness and irrelevance. But there's another way to look at it. The fact that we, collections of atoms that can think and feel and wonder, exist at all is remarkable. We live in a universe that has produced complexity and consciousness, if only for a brief cosmic moment. Perhaps that's enough. Or perhaps life and intelligence will find ways to survive even in this expanding, cooling universe. Perhaps advanced civilizations will develop technologies that allow them to harness the dwindling resources of an aging cosmos. Perhaps they will find ways to create new stars, new sources of energy, or even new universes. The physicist Freeman Dyson once speculated about life adapting to the cold of an expanding universe, evolving to think more slowly, but maintaining consciousness even as the available energy diminishes. These are speculations, of course. We have no evidence that such advanced civilizations exist, let alone that they could accomplish such feats. But the history of life on Earth has been one of adaptation and survival in the face of changing conditions. It's not entirely far-fetched to imagine that intelligence, once it arises, might find ways to persist even as the cosmic environment becomes increasingly hostile. But even if that doesn't happen, even if life and intelligence are fleeting phenomena, in the grand sweep of cosmic history, there is still something profound about our ability to understand the universe and its fate. We are the universe becoming aware of itself, contemplating its own existence and future. There is a kind of poetry in that, a beauty that transcends the cold equations of physics. And so we return to our astronomer, sitting alone in her observatory, pondering the accelerating expansion of the cosmos. She knows that the universe she observes is already changing, already becoming something different from what it was when the light from those distant galaxies first began its journey toward Earth. She knows that billions of years from now, the night sky will look very different, with fewer visible galaxies as they recede beyond the cosmic horizon. But she also knows that the universe is full of surprises. Just as Hubble's discovery of the expanding universe and the later discovery of its acceleration were unexpected revolutions in our understanding, future observations and theories may reveal a cosmic fate very different from what we currently envision. The universe has secrets yet to reveal, mysteries yet to be solved. Where is everything in the universe going? The honest answer is that we don't know for certain. We have theories, models, and evidence that point in specific directions, But the cosmos is vast and complex, and our understanding is limited and evolving. What we do know is that the universe is dynamic, not static. It changes over time, and it will continue to change in ways both predictable and surprising. Perhaps the most profound lesson from cosmology is one of perspective. Our human concerns, our politics, our conflicts, our daily struggles unfold against the backdrop of a universe operating on scales of space and time that dwarf our existence. There's something humbling about that, but also something liberating. We are part of this vast cosmic story, participants in this grand unfolding of the universe. For a brief moment in cosmic history, we have the privilege of observing and understanding a small part of it. And that understanding continues to evolve. Each new telescope, each new particle accelerator, each new mathematical model brings us closer to a more complete picture of the cosmos and its fate. We may never have the final answer to where everything in the universe is going, but the journey of discovery is valuable in itself. Indeed, it's worth noting that the very concepts of going and fate are human constructs, ways of thinking, about change over time that we impose on a universe that simply exists and evolves according to physical laws. The universe itself has no goal, no purpose, no destination. It simply is. The question of where everything is going makes sense to us because we are beings who experience time linearly and who naturally think in terms of narratives with beginnings, middles, and ends. But the universe itself transcends such narratives. It exists across all of time simultaneously, a four-dimensional structure that we experience slice by slice as we move through it. From this perspective, the universe isn't going anywhere. It's already everywhere it will ever be, a complete tapestry of space-time in which we perceive only a tiny fragment. This perspective, sometimes called eternalism or the block universe view, is supported by Einstein's theory of relativity, which treats time as a dimension similar to space. According to this view, the future already exists in the same sense that distant places already exist. We can't see or experience that future yet, just as we can't see or experience distant galaxies except by waiting for their light to reach us. But it's there nonetheless. Of course, this philosophical perspective doesn't change the physical predictions about the expansion of the universe and the long-term fate of matter. Whether we view the universe as evolving through time or as a static four-dimensional structure, the pattern of that evolution or structure remains the same. Galaxies recede, stars burn out, entropy increases. But the block universe perspective does offer a kind of cosmic consolation. If all of time exists eternally, then nothing is truly lost. The past, the present, the future, they all exist as part of this vast cosmic structure. Our brief moment of consciousness, our civilization, our planet, our star, they are all eternal parts of the universe, preserved in the amber of space-time. This may seem like cold comfort against the backdrop of an expanding, cooling cosmos, but it reminds us that existence itself is a kind of miracle, a fleeting arrangement of matter and energy that allows the universe to perceive and understand itself, if only for a moment. Where is everything in the universe going? In one sense, nowhere. It's already there. A complete four-dimensional structure that includes all of past, present, and future. In another sense, everywhere, spreading out across an ever-expanding cosmos. And in yet another sense, here, existing in this moment, in this place, in this configuration of matter and energy that allows us to ask the question in the first place. The true answer, perhaps, is all of these and none of these. The universe is stranger and more wonderful than our limited human concepts can fully capture. But in our efforts to understand it, In our questions and theories and observations, we participate in one of the most remarkable aspects of the cosmos, its ability, through us, to wonder about itself. You've been watching the entire history of the universe. Don't forget to like and subscribe, and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.